All right. The structure of calculating confidence intervals for population proportions is very similar to what we did in section 8.1 for confidence intervals for population means, right? We're still, you know, formatting our confidence intervals, with a point estimate plus a margin of error, right? And we can have it in these three different formats that you see here, here, and here. Okay, so that part hasn't changed. That kind of still remains the same. And the origin of how these confidence intervals are derived also remains the same. I realized I should have included right here in front of this square root. I should have put the Z alpha 2 score in here. So kind of add that into your notes. But basically, error is equal to the Z alpha 2 score times this quantity here, the square root of P prime Q prime divided by N. So multiplying these two together gets you this error, and you add the error to give you the upper bound for your interval, and you subtract error from your point estimate to give you the lower bound of your interval, and that creates your interval or your range of values that has a certain confidence level of containing your population parameter, your population proportion. So let's just jump right into doing an example. So suppose that a market research firm is hired to estimate the percent of adults living in a large city who have smartphones. 500 randomly selected adult residents in this city are surveyed to determine whether they have smartphones. Of the 500 people surveyed, 421 responded yes. Using a 95% confidence level, compute a confidence interval estimate for the true proportion of adult residents of this city who have smartphones. Okay, so let's first look at our given information. So let's see here. Market research firm is hired to estimate the percent of adults, blah, blah, blah. 500 randomly selected adult residents. Okay, randomly. So I think this implies we've got a simple random sample. So we have a sample size of 500. Now, we need to start thinking about in terms of proportions, right? So a sample proportion is successes over a total number of trials. Now, we already have our total number of trials or sample size, which was 500. So we need to be on the lookout for how many successes we have. All right, and it says of the 500 people surveyed, 421 responded yes. So we're considering a yes to be considered a success. So our value of X is going to be 421. All right. Using a 95% confidence level. So we have a confidence level of 0.95, which means we're going to have a significance level of 0.05. And since that's going to be two-tailed, we're going to divide that by 2. So each tail is going to have an area of 2.5%. Compute a confidence interval estimate for the true proportion of adult residents of the city who have smartphones. So we're just trying to figure out, the interval for the proportion of adults at large that own smartphones. All right, so I think that's about all that we can glean from the given information. So let's look at what we need. Well, we need to construct a confidence interval. And for this confidence interval, we need the sample proportion, which we're going to be able to get because we have everything that we need in order to calculate it. So we got that. We'll have to just do a quick calculation, but we can get it. But what we don't have is the margin of error. That we'll certainly have to calculate next. Okay, so P prime, the proportion of successes in our sample, is going to be equal to the number of successes of our sample over the sample size. And so that's 421 all over 500, which comes out to 0.842. So we have a P prime value of 0.842. And we need to calculate Q prime. Well, Q prime is 1 minus P prime, which will be 1 minus 0.842. And that'll come out to 0.158. Okay, so if we just do 1 minus 0.842, do this on your calculator, you should get 0.158. All right, so we have P prime and Q prime. The reason why I went ahead and did Q prime is we're going to need that for our margin of error. All righty. So now let's calculate margin of error. So the equation for our margin of error is going to be Z alpha 2 times the square root of P prime Q prime divided by N. All right, so Q prime we got, P prime we've got, N we've got, but what we still need is we need this Z alpha 2 score. So let's do a quick little sketch here off to the side. It's going to be two-tailed with a confidence level of 0.95. And we're going to have a positive Z critical value and a negative Z critical value. Significance level divided by 2 is 0.025. That's the area in this tail. Significance over 2 is 0.025. That's the area in this tail. And to convert an area into a value on the number line, we need to use our inverse function. On the Texas Instruments, we'll have an area of 0.025 with a mean of 0, standard deviation of 1. And go ahead and use the value on the right. That'll give us a positive Z critical value, which we can then just directly plug in here. On the NumWorks calculator, again, a mean of 0, standard deviation of 1. Area to the right, which is this third option, with an area of 0.025. And what that should get you is that should get you a Z critical value of 1.960. I'm going to go ahead and put these in, and I'm going to save these into variable Z into both, so I can use that here in this calculation. So let me come over here, go ahead and clear this stuff out from the previous stuff. All right, so distribution, inverse norm, 0.025, mean of 0, 1 to the right. It'll be a positive value, so I can go ahead and store that. Alpha 2, which will put a z. Got it. All right, let me come over here to the numworks calculator. I'm going to go ahead and clear this out. And I want to go to the distributions app. I'm in the students t distribution, so I want to back out of that so I get to normal. Okay, mean of 0, standard deviation of 1. And I want the area to the right with an area of 0.025. Execute. And I want to store this, so shift x to the y. And I want to store that in variable z. I want to do it in capital Z. So shift alpha plus, we'll put a z. There we go. All right. So our margin of error is going to be equal to 1.960. And that's going to be times the square root. Now p prime is 0.842. Q prime is 0.158 divided by n, which is 500. All right, so let's put that into our calculator. So let's see here, I need to put a z, left parentheses. Now I got to put in a square root. And I want to make sure I put parentheses around the units in the numerator. So that was 0.842. So 0.842 times 0. Was that 158? 158. There we go. And I want to divide that by 500. Now the cursor's inside the square root sign, so I want to hit the right arrow once to take me outside of it and put my right parentheses. Now I'm going to leave that up because I want to put this into the numworks calculator. So I'm going to back out and come back up to calculation. And I want to put in the letter Z, so shift alpha plus. And actually, I go back. All right, I can put square root and 0.842 times 0.158, right parentheses, divided by 500. And actually, so I think I don't need to put the parentheses in here. I think I can just go ahead and hit execute and enter. And I get the same answer, 0.0319 and some change. So 0, the error, 0.0319 and some change. So because my p prime here is 3 decimal places of accuracy, I'm going to round my error also to 3 decimal places of accuracy. So that's going to be 0.032 for the margin of error. So if I want to write this as a confidence interval in this p prime plus and minus e format, then p prime is 0.842 plus and minus the error, which is 0.032. Now here we're writing this as like a fractional value. If you wanted to write this as a percent, you would put it as 84.2 plus and minus 3.2%. So you put the percent at the end like that. All right. Now we can check our answers because both calculators can create um, proportional z intervals. So we can put in our values of the number of successes over the total number of trials, our sample size, and our confidence level. We can do the same here with the numworks calculator. So let's see what that looks like and check our answer there. So let's see here. So I think if we hit stat and go to tests, we want a one proportion z interval. Let's see here. Okay, right here. So one proportion z interval. So I'll hit enter. And this was 421 out of 500. And we want a confidence level of 95%. So we can hit calculate. All right. So it uses p hat, like a little caret across the top instead of an apostrophe, and you'll see that sometimes. So p hat is our sample proportion. It's 0.842. That's what we calculated. And we get this range. So let me show that on the numworks calculator here. So I'll go to home. Now we want to go to the inference app. And then we want to go to intervals. And we want a one proportion confidence interval. And here we can put 421 for our number of successes, sample size of 500, confidence level of 0.95. Okay, so it gives us the p prime number, the sample proportion. Again, they use a p hat here. I think your textbook uses p prime, which is where I'm getting that from. The critical value we calculated earlier, our margin of error. Hit next. And so this is showing us the confidence interval in two different formats here. So this is our point estimate plus and minus the margin of error that we calculated. And if you take 0.842 and you add 0.031, you get 0.873. And if you take 0.842 and subtract 0.032, then you get this value, 0.81. So the percentage of adults that are using smartphones is between 81% and 87%, with a 95% confidence level. And I think if you hit up and down, it calculates confidence intervals for these different confidence levels. You can just scroll up and down. So that's kind of neat to see how the confidence interval shrinks with a lower confidence level and how the confidence level increases in size when you have a higher confidence level. All right, so I think that gives us everything we need for this problem. Okay, let me know if you have any questions.